Okay, welcome everyone to our lecture on quantitative risk management, and Happy New Year to every one of you. We stopped right before chapter 8 and we want to continue now with chapter 8, which is based on and related to extreme value theory. Now, to give you a first idea of what extreme value theory is all about, please think about a distribution that looks, for example, like this. And we know the distribution of this data. And what we are interested in now is actually the distribution of maybe this or maybe this data. Now, if you were to zoom in into these points, you would see that this actually, for example, this would look like this. Maybe this would look like this. And this is what extreme value theory is actually all about. It is looking at extreme data points of statistical distributions, taking these data points and coming up with distributions for these extreme points only. And it's quite interesting to see what results we will get here in extreme value theory, because we will see that actually most of these extreme points have limiting distributions, and you can even beforehand or give some information on what statistical distribution these data points follow. Now, extreme value theory, or just EVT, extreme value theory is a large part of statistics in mathematics, but it's also extremely important, well, you could have guessed, for quality control, quality optimization, and in insurance mathematics. Why insurance mathematics? Well, you are in insurance and actuarial mathematics, you are most concerned about those extreme losses, extreme damages, extreme losses in your insurance contracts. And for example, if these are financial losses, you know that these are, for example, these are minor thefts, these are minor car damages, but these are the damages that could really make your business unprofitable. So you're interested in the distribution and modeling these extreme losses. And if it's important for insurance mathematics, it's of course also important in risk management, most notably, I guess, in operational risk management, because this is also where we have extreme losses and we need to think about the statistical behavior of these extreme losses, and that's where we will employ extreme value theory. We'll start with a short introduction, and then we'll see two main approaches to extreme value theory. The first is the block maxima method, and then we'll move on to threshold exceedances. There are many good textbooks on extreme value theory. I think one is by Mikosch and Kluppelberg, and this whole chapter is based on the quantitative risk management book by McNeil Frey Embrecht. They have a very, very good description of extreme value theory and its use in quantitative risk management. But you will get the main information on the slides and here as well. So with the introduction, I've probably mentioned all these points. We are interested in modeling the tails, the extreme points of financial losses, of insurance losses, of financial risks. And it might be that if we have all the data, the distribution follows more or less a normal distribution, but it could be that just at the very end, in the tails of the distribution, the distributional assumption for the whole data sample is not doing so well. So one solution for this is to look at the extreme data points only and to come up with a distributional model for these extreme points, and this gives us extreme value theory. So what is the fundamental problem of EVT? Classical extreme value theory deals primarily with limiting distributions, in German Grenzverteilung, of certain extreme value processes. It means what? It means that you have some data and you probably don't know the distribution, but you at least know that the distribution of these extreme values will move, it will converge to a limiting distribution. And of particular interest are so-called generalized extreme value distributions. So these are hereafter called GEVs. It's one class of distributions for which you can see, and we will see in just a matter of moments, that certain extreme values the distribution of these extreme values will converge to one of these generalized extreme value distributions. So we'll start with the block maxima method. And this is also where we have the central theme of classical extreme value. We start with normalized maxima of independent random variables. So first definition, Mn. We have a sample xi, x1, x2, x3 up until xn, which is our data sample. Should be IID, random sample, and Mn is now the maximum of these observations from 1 till n. And Mn is then called the block maxima. Why? Because if this is the distribution, we can also say this is the first block, this is the second block, this is the third block, and so on. And then we choose the maximum of these points here. And a central result now in EVT will be that the only non-trivial limiting distributions of normalized blocks maxima come from the family of GEV distributions. So we'll see that actually by looking at generalized extreme value distributions, we get the limiting behavior of these block maxima. So let's first define what a generalized extreme value or a GEV distribution looks like. It's a function. It has a distribution function h, xi. Xi is the parameter, and it's defined as the exponential function of -1 plus xi times x, taken to the -1 over xi's power for all parameters that are unequal to 0, and for the parameter being equal, it's just the exponential function of minus e taken to the minus x power, and it should be that 1 plus xi times x is larger than 0. You can also generate a class of distributions with 3 parameters by normalizing this in the following way. You subtract mu, you standardize by the standard deviation or volatility sigma, and then this is the 3 parameter distribution with xi, the parameter that governs the question and decides the question which generalized extreme value distribution you are looking at, and mu and sigma resemble mean and standard deviation, so that you get a standardized GEV distribution. Okay. So xi determines the shape of the distribution, thus it's called the shape parameter. The fact that it's called generalized, it's derived from the fact that the following distribution classes result for different values. Actually, you get the Fréchet, you get the Gumbel, and you get the Weibull distributions for different parameters, xi. And in the following figure, you can see an example of a Fréchet distribution. For example, here you have the shape parameter being equal to 0.5, mu being 0.5, and sigma being equal to 1. You get this Fréchet distribution. Okay. Slightly different one with mu being 0, sigma being 1. Same shape parameter. It's a little bit more tilted to the left, and yet another example of a GEV distribution. Okay. So far we only know what a block maxima is. It's the maximum of a number of observations in this block. And we know what a GEV distribution is, how it's defined, but we do not know how they are interrelated. So we'll start with the block maxima Mn, and we are looking at the distribution function of Mn, and it's then given by probability of the block maxima, Mn being smaller or equal to x, because it is an IID random sample, this is equal to the probability that x1 is smaller or equal than x, x2 is smaller or equal to x, and so on. And again, because we have an IID sample, they are independent, this is the product of all those probabilities that each individual observation xi is smaller or equal than x. And this gives us the product of all those individual probabilities. So F is the distribution of all identically distributed observations xi, and the probability of the distribution of the block maxima is simply given by the product of the individual distributions of each observation xi. Now for unlimited random variables xi, Mn converges in probability to infinity, so that we have to consider normalized block maxima to determine a limiting distribution. So we normalize it. And we say that F lies, we call this the maximum domain of attraction, the MDA, of a non-degenerated distribution function H, if we have suitable sequences Cn larger than 0 and Dn such that the probability of the normalized distribution. So we have Mn, we normalize this in the following way. We subtract a D and we standardize by C, and you can imagine that Dn and Cn are basically the means, the averages, and the volatilities, just like you would standardize a normal distribution. That if you standardize, if you normalize the block maxima, and you're looking at the distribution, this is the distribution. I can see you're writing questions in the chat window. Because I'm recording this, I will not open the chat window. I'll try to answer your question at the very end. This is the distribution of the normalized block maxima. If the limit for n to infinity, so if you increase the number of points in this block maxima, if you increase this and this converges to a distribution function h, then we say that F lies in the maximum domain of attraction of h. So in other words, we know that you can look at the block maxima, and the block maxima, actually the distribution of the block maxima converges to one distribution, which is h. Now, we don't know how h looks like, but we simply know that Mn, the distribution of the block maxima, and n doesn't converge to infinity. Okay. Now, a distribution for which Fn converges to either 1 or 0 is called degenerated. That's what we say if we simply multiply those distributions f n times, and what you get is always 1 or always 0, then we call this degenerated, because this is a trivial example of a distribution function. And now the central result of extreme, right, we can delete this here, of extreme value theory is the Fisher-Tippett-Gnedenko theorem. Now what's that? Without proof, the theorem is given that by if f, the distribution of your observations, if it's in the maximum domain of attraction of a distribution h, we don't say anything about h. If it's valid for a non-degenerated distribution h, then h must be a GEV distribution with a parameter xi. So this is the main theorem, the first main theorem in extreme value theory. What does it tell you? It means that if you're looking at a random sample, x1, x2, x3, and so on, if x is distributed according to a certain distribution f, and if f doesn't degenerate when you're looking at the block maxima, if it's in the maximum domain of attraction of a distribution h, then h must be a GD distribution. So you actually know that if you take the block maxima, if you normalize them, if you see that actually for this distribution of your observations, F, this is the full observation we were talking about here. This would be F. And if F is in the domain, maximum domain of attraction of a function, of a distribution function H, then H must be a GEV distribution. And obviously, the sequences Cn and Dn used for normalizing the block maxima, they influence the parameters mu and sigma of the respective GEV distribution. And the limit behavior of the block minima is also the same. It's also covered by the theorem. So what do you get? You start out with your observations. You start out with your distribution F. You are looking at block maxima. You're splitting up all your observations into blocks. You're looking at the minimums or the maxima. And if you're looking at if you are interested in the distribution of your block maxima or block minima equivalently, you actually know that in this case that F, the distribution of your observations, of all observations, if it's in the maximum domain of attraction of a non-degenerated distribution, you are getting a generalized extreme value distribution for your block maxima. So this is quite surprising. So let's look at some examples. If we have exponentially distributed xi, where the distribution function f is given by a 1 minus exponential function of minus beta times x, you get with Cn being 1 over beta and Dn being the logarithm of n over beta, you get the limiting distribution of the block maxima being an exponential function of minus e of minus x. Thus, f lies in the maximum domain of attraction of a GEV distribution with a parameter, shape parameter 0. For Pareto distributed xi, we have a slightly different function f. Again, you need to show that not in the exam or in the, obviously not in the modeling task, but you can look up that for some distributions, like for example here the Pareto distribution, you can show that actually the Pareto distribution f, the block maxima, f lies in the maximum domain of attraction of a GEV distribution, and this time you get a slightly different parameter, it's 1 over alpha. Okay, so this is known, and at this point we know how the extreme values in the form of block maxima are actually distributed. We know that if f is in the maximum domain of attraction of a GEV distribution, we can immediately give the distribution of the block maxima. Some additional properties. Now the shape of the distributions that lead to a particular type of MDA, they can also be characterized. For this, we first need the definition of a slowly varying function. And we say that L, a positive measurable function on the non-negative real line, is called slowly varying if the limit of x going to infinity of L of tx divided by L of x is 1 for t larger than 0. And it means that slowly varying functions are functions that grow relatively slowly with increasing x compared to a power law function, like for example y equal to a times x taken to the ith power, for example the logarithm of n of x, sorry. So it's a function that is slowly or increasing slower or more slowly than a power law function. Now we also have a regularly varying function, a positive measurable function h on the non-negative real line is called regularly varying with index rho if the following applies: limit of h of tx divided by h of x is actually the rhoth power of t, and what you can see is that regularly varying functions can be represented as a power law function multiplied by a slowly varying function h. And with these definitions, we can now characterize, for example, the distributions that lie in the maximum domain of attraction of a Frechet distribution. This is the theorem of Gnedenko. For the Fréchet case, so for the parameter xi or xi being larger than 0, we get the following equivalence. F lies in the maximum domain of attraction of a Fréchet distribution if and only if the survival function is given by x taken to the minus 1 over xith power times a slowly varying function. And the statement of the proposition is now that distributions within the maximum domain of attraction of a Fréchet distribution have regularly varying tails. More precisely, the tails decrease like a power law function. And for the other cases, so shape parameter being equal to 0, shape parameter being smaller than 0, we have similar theorems. However, Fréchet case is of particular importance because it includes distributions with heavy tails. So the tails are heavier than in the case of a normal distribution. Okay. Now, it's important to note that this only applies to IID distributed random variables, to random samples. If we have a time series, if we have weakly stationary time series, you can transfer some of the results, but it's more difficult with time series models, because in these cases, your random samples are not IID. That's clear. So in other words, in this theorem, F is the same for all x1, x2, x3. And if you have a weird time series that is non-stationary, this is no longer the case. So each observation in many of these block maximas, in these blocks, they don't have the same distribution F. They have different distributions, and then this whole theorem falls apart. Okay. So let's look more closely at the block maxima method and how it can be used. Well, suppose we have a record of an unknown distribution F, for which we assume that F is in the maximum domain of attraction for a GEV distribution. The data set represents realizations of IID distributed random variables, or maybe they could have also originated from a Gauss process. We know with the results of the previous section that the true distribution of the n block maxima, Mn for large n, can be approximated at least by a GEV distribution. It's not exactly a GEV distribution, but for increasing n, it will converge to a GEV distribution, and thus we can use it as an approximation. And this result can now be used by adapting a GEV distribution to the data set of the n block maxima. And for this, we need repeated observations of the maxima so that the data set is divided into m blocks with n observations. So what do we do? In some cases, there can be a natural starting point for the division of data. For example, if you have daily returns, you can divide it into months, quarters, or years. So each block will be a month, and in each block you have daily returns. And then we can designate the maximum of the block J with MNJ, so that the complete data set is given by MN1, MN2, MN3. And this only means that, for example, we have blocks of, say, 20 trading days for each month. And then this would be M21, first month, M22, that would be the second month of daily observations, and so on. And the parameters of a GEV distribution can then be estimated using maximum likelihood. There's a typo here, where the log likelihood function is simply given by the sum of the logarithmic density function values of the GEV distribution, and you have to include those observations of the block maxima in the density function, take the logarithm and sum it all up, and then if you maximize this log likelihood function, you can try to estimate the three parameters xi, mu, and sigma. And this is obviously the h, small h, xi, mu, sigma of x is the density function of the GEV distribution we are looking at. So let's make an example. I think this makes it more interesting. We'll look at the example of a record of NASDAQ returns between 94 and 2005, and we are now interested in the distribution of those extreme returns. You can take the QRM lib R package, might have changed a little bit, but it should still be included in the QRM library for the QRM textbook by McNeil Frey Embrechts. So load it, look at the NASDAQ data, use the command N returns equal to minus MK point returns of NASDAQs. So you get their log returns, but reversed in sign. And these are the returns. You can see daily returns between 94 and 2004. And you have some returns that are even minus 12%, some returns plus 10%. So everything's included here in the data. Now let's continue. We can then determine the monthly maxima by using this command aggregate monthly series and returns function equals maximum, and we get as nights the monthly maxima. I think nights is not correct. I don't know what nights is supposed to be. As results, we get the monthly maxima of the negative log returns. So here you can see those monthly maxima, and this here in 2001 was the maximal negative return we have also seen here. So probably this observation is the block maxima of, say, maybe this month. This is half a year already, but you can see this is probably this month. Okay. So these are the block maxima, and we now need to model this. Finally, we extract the data series that is actually of interest from the time series using the monthly data, and we now fit a GEV distribution to these data, and we write the results of this fitting into mod 1. Fit point GEV is already the log likelihood fitting of a GEV distribution, and as you can see, we're using the monthly maxima data, the monthly block maxima, as the input data for the log likelihood estimation, and as a result we get xi hat, mu hat and sigma hat, those three parameters, and they are now estimated based on the block maxima of this data. So the result is actually a Fréchet distribution with heavy tails, not surprising because we have stock market data. And this is the result. So we are interested in the extreme returns in each month, and this is the extreme value density, the generalized extreme value density function for these monthly extreme returns, the monthly maximal returns from the NASDAQ data. Quite interesting. Remember again that we switched the sign, so actually this here would be a 20% loss. So we are looking at losses, and this is a 10% increase. So as you can see, the monthly extreme returns are distributed according to this Fréchet distribution. Okay. Now, we can also estimate some risk figures and risk measures. Let's call them risk measures. Figures is rather weird. Based on this GEV distribution. We can calculate, for example, the so-called return level. So let H be the true distribution of the n block maxima. Then the kn block return level is defined as Rmk, defined as the 1 minus 1 over k quantile of H. And the return level can then be interpreted as the value that is exceeded on average once in one n block within of k units. So for example, R130 in our example is the level that is exceeded only every 100 months. Okay, so maybe we'll stop here for a moment and I can answer your questions from the chat window. Okay, so we've talked about the block maxima, which is very simple first step in extreme value theory. And the block maxima works as we've seen like this. You take the blocks, you divide your sample into certain blocks, you look at the maxima or minima, and then GET Now, EVT, extreme value theory, tells you that what is results for the distribution of those block maxima is a GEV distribution. We now extend this a little by looking at so-called threshold exceedances, which simply means that we are not looking at the maxima of certain blocks, but we are looking at values that exceed a certain threshold. So it's an extension of the block maxima method, and this is what we'll be looking at here in section 8.3. Now, the block maxima method has one main disadvantage. It's comparatively wasteful with the available data. Why? Because we build our blocks and we are only looking, in each block we are only looking at one observation. So it might be that in our example we've just seen with the NASDAQ data, we actually have a lot of data available. But if you have fewer data points available, it might be that you end up with just 3 points, 3 block maxima, and you cannot sensibly estimate the GEV distribution based on this small sample size for the block maxima. So for this reason, we extend this, and this is, I guess, a method that is more frequently used in practice in an industry, is the method of threshold exceedances. These do not exclusively use the maxima of certain subsets, but they use all data points in these subsets that are extreme in the sense that they exceed a certain threshold. For this purpose, not surprisingly, we get a different family of statistical distributions, but they are also related to the GEVs. Now we are looking at the generalized Pareto distributions, or just GPD in short. So let's first again define the later result, what will result as a distribution for those excess and threshold exceedances. The generalized Pareto distribution. It has a distribution function G, 2 parameters, psi and beta, beta being larger than 0, xi being larger or equal than 0. It looks similar to the GEV, and the generalized Pareto distribution includes, as special cases, the usual Pareto distribution, the exponential distribution, and a Pareto distribution of type 2, depending on what the shape parameter looks like. And it also applies that the generalized Pareto distribution lies in the maximum domain of attraction of a generalized extreme value distribution with the same shape parameter. And this is now our main tool we need for modeling threshold exceedances. Some examples for these distributions, for example, here we have shape parameter 0.5 and beta being equal to 1. This is the density function for different betas. You can see the shape parameter is 0.5. They all start at 0, and then they have a slightly different decay to the right. Okay, so in order to arrive at the announced result, which will not be surprising, I guess, we will somehow define excess observations, extreme observations, in the sense that these are exceedances of a certain threshold. The result in the end will be that the distribution of these threshold exceedances converges to a generalized Pareto distribution. We only now have to define all ingredients and then look at the main result. So let x be a random variable with the same distribution, with one distribution f. Same assumption here as before. We have a random variable and we have one distribution f, and the excess distribution over the threshold u could be, for example, if we are looking at this distribution, could be that we say this is where we have u and we are only interested in the distribution of these extreme points. So x is a random variable, f is our distribution, u is the threshold, and for 0 being smaller or equal than x and smaller than xf minus u, this is xf is actually the right endpoint, so this would be the maximal point here. The excess distribution over the threshold is given by fu defined as the probability that x minus u is smaller or equal than x, given that x is above the threshold. So we are looking at the points here, and we are looking at the excess distribution over the threshold u. This can be given by f of x plus u minus f of u divided by the survival function minus 1 minus f of u. And then we can also define the average excess function with finite expected value. This is simply given e, the excess function of u. That's the expected value, the average of x minus u under the condition that x is larger than u. So again, we are only looking at these observations here, and we are interested in the mean, the conditional mean of those observations. This is actually very similar to the expected shortfall we've already seen as a main risk measure. Now, the excess distribution now describes the probability that, for example, if we are in insurance mathematics, a policyholder who has already lived for u time units will die in the interval from u to u plus x. And the average excess function then describes the expected value of f of u as a function of u, that is the expected remaining life as a function of different ages. And for the GPD, both values can be specified directly. Now, assuming that we are looking at a GPD. So for example, the excess distribution is g of xi and beta of u. So the parameter beta is given dependent on the threshold u, and beta of u is given by beta plus xi times u. So it depends on the threshold we've chosen. The excess distribution thus remains a GPD with the same parameter for the form of the distribution and a scaling parameter that grows linearly in the threshold. In other words, if we already start with a GPD, the excess distribution of a GPD is again a slightly different GPD, but we are obviously interested in a more general case in which we don't know that f, or if we have a non-GPD distribution for f, but what results is again a GPD. Now, average excess function can also be specified using the parameters xi and beta. And as you can see, the GPD is relatively invariant to a transition from f to its excess distribution. And that's not a really surprising result, because we will later see that actually the excess distribution is a GPD. This is the famous theorem of Pickens, Balkemer, and de Haan. There exists a positive and measurable function beta for which the following holds, which is the limit superior, that is u, the threshold, moving in limit to the right endpoint. So if, for example, this is the distribution and this is u, if we move u closer to the right endpoint, xf, I hope you can read this. Now, if we are looking at the limit superior of this expression, the difference in absolute values of the excess distribution and a generalized Pareto distribution, this becoming 0 is equivalent to f being in the maximum domain of attraction of a generalized extreme value theory. So what does this Pickens, Balkemer, de Haan theorem tells us? It tells us that the distributions for which the normalized maxima converge to a GEV distribution, they form a set of distributions whose excess distributions for rising thresholds u converge to the corresponding GPD. In other words, it's equivalent. If you have a distribution f, and if f lies in the maximum domain of attraction of a generalized extreme value distribution, this is equivalent to the excess distribution of f converging to a generalized Pareto distribution in case you're moving the threshold closer to the extreme right point. So in other words, if you only increase the threshold enough, at some point the excess distribution will become a generalized Pareto distribution if and only if f itself is in the maximum domain of attraction of a generalized extreme value theory. Now, since almost all distribution types, we've just seen this in our small little break, like for example the Gaussian, the Weibull, the CUNT distributions, all the main interesting distributions in statistics, they all lie in the maximum range of attraction of a GEV distribution. The theorem of Pickens, Balkema, de Haan basically says that if you're looking at access threshold or threshold exceedances, it means that for all major statistical distributions, the excess distribution of the points that exceed a certain threshold, if you only increase the threshold close enough, if you move it close enough to the right endpoint, the distribution of the excess distribution will be a generalized Pareto distribution. So GPD is a natural choice for modeling extreme losses, that is losses, observations over the threshold U. That is threshold exceedances. Okay. I think because we only have 70 slides left and we still have 4 weeks in January, I think this is enough for today. We'll see some examples how we can employ extreme value theory for estimating risks of, for example, financial and insurance losses. Maybe we'll stop here, answer your remaining questions, and then you can have another look at this at home and maybe try out the R programs at home and see if you can make this work. So the idea now is what? With the block maxima, you take your whole data set, build blocks, calculate the maxima, and then use these maximal observations and estimate a GEV distribution. With threshold exceedances, it's choosing a threshold, looking at the observations that exceed this threshold, and then fitting a generalized Pareto distribution to these exceedances. And you're done, and you have an extreme value distribution for these observations, for these extreme losses or these extreme returns. Okay, so let's stop here. Thank you for your attention.